with the, okay. So I want to show you now, which I briefly touched last time, but I want to explain you how our ability to have switches and ability to add capacitors can completely change operation of the transformer. Here, this is an auto transformer, non-isolated, but nevertheless, it is a transformer with a primary and secondary. And some people looked at that, so, oh, well, that's just like if you eliminate, let me see. If you eliminate this switch and eliminate this capacitor shorted, what is this? This is stepped inductor buck, nothing, and nothing new, existed for 50 years. However, I just want to demonstrate you, if you know what you're doing, and if you introduce right components and right place, like in this capacitor in this place, and this switch, extra switch here, then you completely change operation of this magnetic structure. I call this magnetic structure hybrid transformer because it has, as you see, when the switch is on, it has a square wave voltage, input voltage minus output voltage. That's the voltage across the primary, so the square wave voltage across this switch. Now, we just touched upon why the leakage inductance in 60 Hertz is actually desired. What will happen with the leakage inductance here? In original buck converter, tapped inductor buck, without this capacitance and without this switch, you have a switch on and switch off. What happens with this leakage inductance? Energy is stored in that leakage inductance as LR I peak square, so it's energy stored, and then times the switching frequency, how many cycles, that is the power. So you lose a lot of power due to energy stored in leakage inductance. Okay, so you say, well, I'll just make it tight coupling and like 1 turns and foil and then 10 turns on top of it and hope for the best. Well, that won't work because when it's multiplied with a very high frequency, it's going to be a lot of loss, 10%, 20% of the power lost in here. You don't want that. Now the question is, can I make now the transformer, which is actually using this leakage inductance as the part of the circuit and make sure that I make this resonance on the input circuit is this waveform here. So I make this resonant, this leakage inductance, which is undesirable. I make it resonant with these capacitors at the certain frequency, which is here. And do you agree that if this is capacitance on a primary, the same as in a true converter, capacitor on a primary doesn't allow DC current in this capacitor, so the current in this here will have a zero average. It means that during the time that this switch is on, there will be a power transfer this way, but then when this switch is off, during off period, and this one is conducting, in this thing here, there is a primary current during off period, or off period of main switch and on period of this switch. During off period, let's say 90%, this would be resonant current established with these two. Why? Because it turns out you will operating with the dot connection in such a way that this will be shorted. This transformer from primary to secondary with such dot connection will be shorted. So this will be resonant current on the primary. And you know why is that important? because that means this current on the primary, that is a current, okay, that is a current on the, let me show you here. So this current here is a current in yellow. It is a sum of primary current, which is this current, and a secondary current. And what is secondary current? This is a transformer. So if it has a primary current, sine wave, the secondary current will have to be also sine wave. You can see it during off period, multiply with the turns ratio. So that means if this is 2 to 1, this with twice larger sine wave current compared to input. But this sine wave current also has a DC current drawing in the load. So there'll be DC current in the load, which is added to this sine wave current. But both of these sine wave current through the primary and sine wave current through the secondary red, these green and red waveforms add together. In fact, I should have, I guess, use my, let me see. Come on. What happened? Okay. Why doesn't see, that's nice to have a razor, right? Okay. So now this green waveform, and let's put it here this way. So we have now this situation. This green waveform is this current going here, and then the red waveform is this current coming here, and and then the diode current is this sum of the current. And what is the beauty now? I'll give you the kind of anecdote about inductance, okay? Can you see it now? You see what I'm having, right?
Yes, you can see your screen.
Okay, yeah. Back in, there's another anecdote and history. In 1831, Faraday disclosed its law of electromagnetic induction. In 1830, Joseph Henry was professor of Princeton University, and he came independently to Faraday's law, but he didn't publish it, and then Faraday got all the credit. Many years later, Henry also worked in this field, in fact, on telegraphy and so on, and even had some patent disputes with Bell and so on. But the point being is he was at some lecture that someone, at that time, they tried to use this wireless transmission, and Tesla worked with this as well. And then they were using a way to create the sparks. They needed to create the sparks on a transformer and so on. So they tried to do the spikes, and they couldn't generate it. They were disconnecting the circuit to generate the spikes using this inductance, but it just wasn't good enough. Then Henry was in the audience, and he came and he told them, oh, they made inductance, and he used the wire that was used to make inductor and make 10 times more turns. And when you make it 10 times more turns, inductance was increased by turn square, so you had 100 times more inductance. So now if you turn a switch on and off into inductance, sure, you're going to have a big spark, because that's what it is. You are discharging that energy stored in inductance in that spark, okay? But this is opposite what we do here. What happens if I turn the switch on and off? You see, these switches are changing time from being on to off and from off to on. These are two instances when you are turning on and off switches. What happens if the current in this yellow waveform is current in the diode? What happens if the current in the diode is at zero current here and zero current here? Would you mind the inductance, leakage inductance is absorbed in operation of converter. there are no losses, both turn on and turn off losses. And if you make your converter now not to regulate with the duty ratio control, but regulate with the switching frequency, you can force this off period to be constant, and then you change the switching total switching period, which is effectively changing duty ratios. You can regulate and still have, for any operating point, input voltage and operating load current, you still have the same no losses on the diode. It is zero switching losses on the diode. Now, how good is that? What's even better that you can even appreciate. Why? Because if this is now the first converter which operates with a voltage to current. It is not voltage to voltage converter. It is the output current, which is this resonant current here. It has a DC level, and the output current, this resonant currents depend what kind of a peak resonances will be imposed on a diode and imposed on a primary. That means the current, DC load current, dictates the peak resonances. So if now DC load current is dropped in half, all these magnitudes will drop in half. Well, that's exactly what you wanted to do for a microprocessor drive when you have a change of DC load current, sudden change, and then you have immediate change on the next cycle of waveforms drawn from a converter. That's one thing. The other, it is staying at zero current level even at that point. So you can go from a full load to no load. You will not go in a different mode of operation. There is no discontinuous conduction mode. You understand? It was always in continuous conduction. How good is that? Better than you can even imagine. Because why? Once you are in a continuous conduction at no load to full load, you don't have the duty ratio to compensate for change of mode operation, like in the back boost and flyback, that it drastically changes voltage conversion ratio. So now you have a feedback. You don't need a feedback. Why that is good? Well, it's even better, because if you don't need the feedback, then you don't need the limitation of the bandwidth. So your full bandwidth of switching frequency is available. Whereas if you have a feedback, you have in addition the bandwidth limitation. That bandwidth of converter is at best 10% of the switching frequency. So you have 10 times lower bandwidth, and you have no way to allow for quick change of the current, and it's disaster. And what's the solution of our power management companies? Use not one buck converter, use 12 buck converters in parallel to try to operate, to drive a microprocessor drive at 1 volt, from 12 volt to 1 volt. So I always used to say, 1 buck converter is bad enough because it stores energy, as I explained last time. Now you use it 12 times, and you use a special digital circuits to operate this in parallel, right? So how smart is that? Not too smart, right? And are they going to give up on their? No, because they have a business there. They have a business, and they are competing for a $10 billion market a few years ago when I looked at it. And out of this $10 billion market, each of these 50 power management companies make their own version of the 12 buck converters for Intel and all the other IC companies, big microprocessor, and they're all happy. They have 5% of the market, and they don't want anything better, because no one else is better. Their competitors are just as bad as they are, and they are happy to share whatever money they get, okay? And life goes on, okay? So, all right. Hopefully, you'll change that in due course. Now, let me now explain how you can understand this circuit. I try to give you the global picture, and the global picture here is this. Does this transformer as a device has to operate as a square wave voltage and square wave current? I did that in a true converter 45, 46 years ago, but it doesn't have to be. Now I'm showing that for the first time, look, for the first time, we are able to take care of a transformer that its built-in leakage inductance is not the problem, it is a solution. You see what I'm saying? Because in all other converters which have isolation transformer or tapped inductor or you name it, look, without this capacitance and without this resonance, just this switch and this in a buck, energy stored in leakage inductance will be huge. And at the moment of switching, there'll be huge jump in the current, and that jump in the current must be killed by some kind of a very fancy snubber to kill all that leakage energy. And that won't be pretty. And it won't lost a lot of time and a lot of bad waveforms. Here, you have, isn't that beauty? You have a transformer, which unlike a Faraday, or Tesla, Faraday's original idea, or actually Tesla's in an AC generator in AC current, it has a square wave voltage drive and sine wave current, both primary and secondary, and this switch now is forced to have zero switching at all operating points. And then, of course, there's a way that we can make this at the zero voltage high switching, and then you have now another benefit, and you can operate. Listen, you can now operate when you are at 99% efficiency. You don't need to regulate with the duty ratio because it's automatically giving a good regulation, no change of operating point. So you can operate it open loop, no stability problems, no bandwidth limitation, no change of mode of operation. Oh, one more thing, I forgot. What will happen if I put two converters like this next to each other, operating from the same source and to the load, but this converter is identical to this one here, but what? It's made to be delayed from the first one by 50%. So one current will be this yellow and the other current will be this yellow. If you add them together, what are you going to get? Small ripple current. So how is bad? From something, two converters, not 12 buck converters, two of these identical converters. We have a pin, sync pin, which says one is sync for half a period from the other. What do you get? No capacitors needed on the output. How good is that?
Some are required, but like way less than usual. Just
and even better. What is even better?
Yeah.
Oh, listen, what is even better? What about this capacitor? Does it have to be large?
No, actually, yeah, like 2.2 microhenries, microfarads.
The point is this we have to talk about these capacitors in terms of its voltage rating, DC voltage, and in terms of this RMS current. Now, what about RMS current here? If this is a 10 to 1 step down in the voltage, this is 10 to 1 step up in the current, which means opposite, it is 10 to 1 step down in the current from this 100 amp, this becomes now 10 amps. So this capacitor delivers 100 amp output, actually more, 200 amp, because two of them in parallel, each one will be delivering 100 amps, so it's 200 amps, but this capacitor will be 10 amps. What about its voltage? If this is 100 volts, doesn't have to be, it's not 100 volts because this capacitor will be D times VG. So its duty ratio is 0.1. This capacitor will be 10 volts. So its magic happens. Capacitance is rated as power 10 times less than input voltage, 10 times less than output current, so 100 times in power and carrying 100 times higher power. So how bad is that? Okay. So I'm telling you the importance of converter system, or topology and mode of operation. The hybrid switching, what I call this, and hybrid transformer, this is it. And it has why I call it hybrid switching and hybrid transformer. Have you ever seen a converter with the 3 switches? I worked with my PhD student back in Caltech when we originally started assuming that All converters come because you have inductors and capacitors like in a true converter. So while inductance is storing energy, increasing current, capacitor is releasing energy, discharging. So they work in unison. Store, restore, charge, discharge the current, and charge, discharge the voltage, and so on. So we never even considered 3 switches. Here is an example that the 3 switches are actually beautiful, right? It's not like 4 switches and 6 switches, 8 switches in pair like a full bridge. 4 switches, a transistor on a primary, 4 diodes in a secondary, 8 switches. To just get isolation, it's just have 3 switches and get all of these features. Now comes what I promised, but I'm gradually running out of time. So let me finish this presentation and remind you where I'm going ahead with it. I'm just showing you that after I came up with this square wave drive or rectangular drive of current, rectangular voltage in a true converter, here's another example when a voltage drive is a square wave and current on a transformer sine wave. But what's the difference? Sine wave currents are not 60 hertz. They're 60 kilohertz. So therefore, but of course important is it is not 600 kilohertz and not 6 megahertz. I don't need that. 60 kilohertz is plenty enough. And as I mentioned last time in my presentation, we failed dramatically in the power electronics. When I started, we were excited to say, oh, we had 4 kilohertz bipolar. We can't wait to get to the 20 kilohertz. And then 50 hertz transformer to 20 kilohertz will be 40 times smaller. And then we went from 20 kilohertz because of this wrong way of fake inductors, which are not AC inductors, but DC inductors. We went to 200 kilohertz and 2 megahertz and now 20 megahertz. And did we get any reduction in size? Zilch. We increased the frequency 1,000 times and we don't have any size reduction. That's number one. But the bigger problem than that is not only we don't have any size reduction, we don't have scaling of the power. We are not allowed to scale power because we are limited with the current of these inductors, and therefore we are limited with the eventually the power we can process. And as I pointed last time, all classical converters have another big problem. They have big inductors, they store energy, like back type inductor in the output, and that energy requires that the core is 2 or 3 core sizes bigger than a core used for decent transformer. Okay? And it's not needed. And it's limiting the current and limiting power converter. Certainly, you won't be able to make a forward converter with a, even 100 kilowatt, let alone megawatt or so on, right? Because you have a current and power limitation. So let me now see the analysis of this and how this converter works, that essentially the connection you are making it, you are for certain off time period, you are making the transformer, which seems like unheard of, short. And I'll explain you why.